Next up is binding energy. So the energy that binds the nucleons together is called binding energy. And we can use Einstein's equation, which should probably look familiar, to calculate this. But the first thing that we need to do is look at mass defect. So the energy that is required to hold these nucleons together, when they get together, some of the mass of these particles is converted into energy. So mass and energy are interconvertible. And also, some of the equations are going to require you to use the mass of the electron. Now, I know previously we spoke about the mass of the electron being negligible, and while it is, some of the calculations are going to want you to remove that from the nucleus, even though it's not going to make much of a difference in your calculation. So I'm just going to do that to show you what you might find. And that's the way your book does it, so we'll just do it that way. They're doing that because we're looking only at the mass of the nucleus and not at the mass of the whole particle. So when you're given an isotopic mass, it's generally the mass of that whole isotope, which includes the electrons, and this focuses solely on the nucleus and the nucleons. And since only particles that are considered nucleons are those in the nucleus, we need to remove the mass of the electrons first. So to find the mass defect for copper-63, and we're given the mass of the isotope as 62.91367 U, and remember U is equivalent to AMU. And the mass of a proton, 1.00728 U, and the mass of a neutron, 1.00867. Then I gave you the mass of the electron and the speed of light. So in order to do this, first we need to know the number of protons, the number of neutrons, and the number of electrons. All right, protons, we look for a copper. Copper is number 29, so there are 29 protons. We take 63 minus 29, and we get 34 for the number of neutrons. And because this is neutral copper, the number of electrons and the number of protons are going to be equal, so the number of electrons is 29 as well. So the first thing we're going to do is we're going to take this isotopic mass, and we're going to subtract the mass of 29 electrons. So that's what we're going to do first. 62.91367 U minus 29 times the mass of this for the number of electrons. And when we do that, we get 62.8977606. So this is the nucleus, just the mass of the nucleus. Yeah, that's an A. Once we have the mass of the nucleus, we're going to subtract the mass of all of the nucleons. So we're going to take 29 times the mass of a proton plus 34 times the mass of a neutron. So when we do that, 29 times the mass of a proton, 34 times the mass of the neutron, and we're going to subtract from that the mass that we were given for the nucleus minus the electrons. Now I walked you through all this and did the 29 is times 1.00728, and this is what we get for both of those. I added them together, we got 63.5059, and we're going to subtract from that the mass of the actual isotope that we have. So here is the difference. This is called mass defect. So this is in fact the mass difference, or the mass defect. So that is the difference in the amount of mass that from what we should have compared to what we do have. That's how much mass was converted to energy. Once we have that, we can take this number and we can put it into E is equal to mc squared. So we put the deltas in there, it's okay. All right, so we take the mass defect, 0.6081394, but this is in U, so I'm going to need to do some unit conversions first. So let's go on to the next slide and we'll look at some unit conversions that we might have to do. And if you're looking for these in this particular book, they're on page 908. Some common unit conversions you might have to do for mass defect is what we're going to start with, are U per atom to grams per mole, or U per atom to kilograms per mole. Now, we're going to be starting with the previous example where we had U per atom. So we'll try this and we'll go to grams per mole. Well, let's start by writing down 0.6081394 U per 1 atom. One U is 1.6605 times 10 to the negative 24th grams. This is going to be given. All right, so that's a conversion factor. The U's cancel. Then we want to go per mole. So how many atoms are in a mole? Right, 6.02 times 10 to the 23rd atoms are in a mole. So if we do this calculation, multiply across the top, divide by the bottom, we're going to end up with 0.6079 089152 grams per mole. All right, we're not doing a whole bunch of with sig figs right now. I think this is heavy enough for you. Change the colors here. What if I want to go from U per atom to kilograms per atom? 0.60081394 U per atom. So we're starting in this same spot that we left off in on the last slide. These are just unit conversions. And 1 U is 1.6605, but instead of being times 10 to the negative 24th like we had here, it's going to be 3 higher, times 10 to the negative 27th to go from grams to kilograms. Calculate that, and we get 1.00981547 times 10 to the negative 27th kilograms per atom. Kilograms per atom. Well, I'll tell you why we might want that in just a moment, but for now, let's look at what's written next. So here, once you get to the energy, well, we wrote that on the last slide. Oh, you know what? But we didn't actually end up doing it, so that disappeared on me, but we had this calculation, right? And we took this and we're going to put this into delta E is equal to mass defect times C squared. But that's where we came to a problem where we were in U and the unit wasn't going to make much sense. We can still do the calculation, so we can do that, but it might be easier for some of you just to change this first. If we change it into kilograms like we just did on the next slide, we can actually use this. So let's just look at the units. So if we're going to do the calculation, E is equal to mass defect times C squared, we're going to end up with our mass units here, kilograms. We don't have to be per atom right now. We can actually drop that if we want, but we're going to have kilograms, and C is the speed of light, 2.9979 times 10 to the 8th meters per second. And we're going to square that. So we're going to have kilograms times meters squared divided by seconds squared. And maybe that doesn't look familiar to you. You might want to log that away somewhere in your brain, but that is equal to a joule. And joules are an energy unit. So we're going to end up with joules per atom when we do this using kilograms per atom or kilograms. Now I'm going to erase that because I know you can pause it and go back if you want. So I'm going to erase that, and we're going to calculate E for what we just did on the previous slide. Hopefully none of you are red-green colorblind. I'm going to use green. Okay, so delta E here is equal to our mass defect times C squared. So we have 1.00981547 times 10 to the negative 27th kilograms per atom times 2.9979 times 10 to the 8th meters per second squared. So what cancels here? Nothing. Okay, good. That's a good sign. We're going to end up, we do that calculation, and we get 9.07562004. It's bothering me not to do sig figs, but we'll get over it, right? Times 10 to the minus 11th. Now, remember, kilograms, meters squared per second per atom, times second squared is joules per atom. Okay, so I'm going to erase that and just change that to joules per atom. So now we're in joules per atom. Once we're in joules per atom, we might be asked to go to joules per mole, and we would do the same step here to go to joules per mole. If you want me to do that, I can try and move this over. Hopefully I don't have a typo. So put my equal sign over here. What did we have? 9.07562004 times 10 to the negative 11th joules per atom. And we have 6.02 times 10 to the 23rd atoms per mole. So we do that calculation and we have, 9.07562004 to the negative 11th times 6.02 times 10 to the 23rd gives us 5.46. I'm going to have to round this. There's no way I can keep all these numbers. 5.4635 times 10 to the 13th joules per mole. But taking this joules per atom, and let's ask ourselves, what is this atom that we're talking about? Well, really, we subtracted the electrons, so the atom we're talking about is actually a nucleus. So joules per atom here in what we're talking about is actually equivalent to joules per nucleus. Now, if you hadn't subtracted out the electrons yet, you would want to do that at this point, because going from an entire atom to the nucleus, technically we would have to be subtracting out those electrons. But we already subtracted those electrons, so we're okay. And our joules per atom is going to be equal to a joules per nucleus, so we can just change that unit. They're 1 to 1. So this is going to be equal to, we'll say equal to each other here. And we might want to go to joules per nucleon. How many nucleons are in copper 63? Has how many nucleons? Has 63 nucleons. Number of protons, number of neutrons. So we would take our number for joules per atom, so 9.07562004 times 10 to the negative 11th joules per atom becomes joules per nucleus. And for every one nucleus, there are 63 nucleons, right? So I have to retype that in there, 9.07562004 times 10 to the negative 11th divided by 63 gives us joules per nucleon. And we could grab that number real quick. It's not going to be our final answer usually. 1.44057, I'm just going to round it, 6 times 10 to the negative 12th. And this is joules per nucleon. But why we're talking about nuclear chemistry is we're talking about the large energy changes that we see. So in order to make it easier, usually we compare using electron volts. So electron volts is EV, or 1 million electron volts, MeV. So one of those, I'm not going to put an or here, I'm going to keep that over here, 1 million electron volts, MeV, is equal to, this is just 1 MeV, is equal to 1.60 times 10 to the negative 13th joules. So we can take this joule and get to how many million electron volts are we going to get per nucleon. So we can calculate how much energy we're going to get from this. Whether you're going to war or whether you're going to a power plant, this is going to be what it boils down to. We want to know how much energy we're going to get from the reaction. So 1.440576 times 10 to the negative 12th joules per nucleon, per one nucleon. And there are 1.60 times 10 to the negative 13th joules for every 1 million electron volts. So we're going to divide the 1.440576 times 10 to the negative 12th by 1.60 e to the negative 13th, and we get 9.003599131 MeV per nucleon. So for copper 63, we're going to end up with 9 MeV per nucleon, essentially. I know I didn't make you do sig figs throughout all that. I think that was enough new stuff right there for you. We'll focus on sig figs, but you would follow all the same sig fig rules, multiplication, division. We got some addition and subtraction in there too. Those are some pretty big unit conversions that you might have to do. Binding energy has a maximum result usually around iron. So we see the nuclear result, the result of this may be maximum in nuclear stability increases when our lighter elements fuse together, and that's going to, you're going to see, okay, look at the red arrows. So when our heavy elements split apart, this is going to be called fission. And when our lighter elements fuse together, that's called fusion. We see it coming to this maximum head of stability around iron 56. And so that's where we see the most bang for our buck, essentially. So nuclear fission. Fission means to break apart. So we take these fragments of heavier nuclei and we break them apart into smaller pieces. We do that by striking them with neutrons. Aren't we nice? We just crash these neutrons into these atoms and see what happens. Well, what happens is the atomic nucleus splits into 2 nearly equal mass fragments. And with it comes a tremendous amount of energy. Now, this can be good depending on what type of conditions it's under, and hopefully it's not at the end of somebody deciding they want to attack somebody in a military way. But we can actually calculate the amount of energy that's released, like we just did, using Einstein's equation and mass defect. Okay, and this was first given evidence in 1939 by Hahn and Strassmann. I'll mention a little bit about them, but I'm not gonna, you guys can look this stuff up if you really want to. It's also some of it in your textbook. So this is a nuclear fission reaction. We see the let me change colors here. We see the neutron here coming in, and it's going to smash into the uranium nucleus. Now when that happens, it smashes into the nucleus and we get two nearly equal sized parts, and that's what you see here. We got a krypton nucleus of 92 and a barium nucleus 141. Okay, well, they're not that close, but they're relatively equal sizes. But also, this is a really important part. We get 3 more of these neutrons. And this is almost never the same, what they break apart into. It's very different. And when we get those 3 neutrons and the 2 times 10 kilojoules per mole of that we're seeing here of energy, that's a pretty big reaction. So this is one of 2 of the most important nuclear fission processes. So this is starting with uranium-235. The other one would be plutonium, plutonium-239. These are 2 of the most important ones that we look at. So this is brought about, we call this bombardment, and it has slow thermal neutrons. What happens next is something like this. So it strikes it, we get those neutrons, that slow one that comes in, and when it strikes that uranium-235 nucleus, it's absorbed, and it forms a metastable uranium-236 usually. I can't find it in the picture, just meaning it's partially stable. So we see those, these are around 235 uraniums here. So it's our target uranium-235 and a projectile which it launches, which is the neutron. So it does have that 235, but it also has a neutron that's getting launched out. And when it's going to hit, that other neutron is going to hit this nucleus, and then it's going to break apart into 2 pieces, and that one projects those neutrons as well, which hit another piece, and that's why it's going to keep reacting. The number of neutrons is going to increase very rapidly during the fission process, and it's going to cause more and more fission reactions, resulting in what we call branching chain reactions. The extent to the chain actually depends on the size of the uranium sample. If the sample is too small, it can't sustain the chain reaction, and that's going to be referred to as subcritical. I'm going to change that, that's too bright. That just means the sample is too small. But a sample size that's just right, you know, the 3 bears, right? This one's just right is called a critical sample. But if a sample size is too large, it becomes supercritical. And in samples like that, the fission reaction increases exponentially, resulting in usually a tremendous explosion, a nuclear explosion, and it releases enormous amounts of gamma radiation. I'm laughing a little bit, but that's just the sheer amount of energy that's produced by these reactions is amazing. But we use these a lot in nuclear reactors, and the rate of this fission reaction is controlled so that the number of neutrons that we produce is equal to the number that's absorbed, so it's not getting out of control. It's just enough to sustain the fission reaction. The core in our nuclear reactor consists of fuel rods. You may have heard of fuel rods being transferred or something like that, and they contain uranium-235. And then they also have usually control rods, and the control rods usually contain cadmium. Those are placed between the fuel rods so that if the number of neutrons emitted increases for some reason, those control rods are lowered and they can absorb the excess neutrons, and it'll slow down the fission process. So we have control and somewhat, you know, I mean, not somewhat, I mean, they're very controlled processes that have to be watched and very carefully brought about, I guess is what I should say, and making sure that we follow all of the safety procedures. If you're going to be working, you go work for one of these labs somewhere, make sure you're paying attention and do the right thing. Follow your safety procedures because things can go bad very quickly if you don't. Because if the number of neutrons falls too low, the control rods can then be removed and the fission reaction can increase, but we don't want to get to that subcritical sample part. So the reaction we said starts with a slow, this is the one we said about it's slow thermal neutron that's starting it, but the neutrons that are produced by the fission reactions are fast neutrons, and those can't cause fission reactions on uranium-235. So slow or thermal neutrons are the ones that are required to bring about a fission reaction with uranium-235. These, as you can imagine, heat up very quickly, and you need to have cooling, cool this down. And normally we use a cooling water system, and that slows down the neutrons that are produced by fission, and then they're fed back into the reactor core to bring about more fission reactions. So this would be a nuclear power plant. This works really well. We get a lot of energy produced. These are the control rods we talked about. They can be raised and lowered. These are the fuel rods in here. This is the reactor. And notice that we're pumping water here. And the steam is actually what is produced and turning the turbine to get the electrical output. So we're still using steam power. Even after all these years, we're just getting our steam through a different way. So we do need a large water source. It's very important, but can also be problematic, as we'll see with what happened, a few years ago when we had a tsunami, right? So 27 degrees comes in, the water comes out, it cools this area and comes out in 38 degrees. This is a steam condenser for the turbine. That water is going to come back out down here, go up. Some of it's going to go out as steam, but the other water is going to come down through the pump. It's going to cool that off. So this water is circulated back through, but it's not really touching anything that it should be contaminated with. So what happens after a few years, though, is the concentration of the fission products that capture the neutrons, they build up to a point where we can't really use them for power and we can't produce power at a practical rate. So the fuel rods need to be replaced. This is what worries people. And the fission products that are used in fuel, they contain too many neutrons. And we know that things that contain too many neutrons are unstable, so they're radioactive. And they're going to continue to be dangerous and radioactive for many years, actually many thousands of years. So how do we dispose of this is an enormous problem. Even though this is a great way to get energy, the fuel rods, how do we dispose of them? Where do we keep them? So one reasonable suggestion that came about is with radioactive waste is that it can be converted into a small volume of glassy materials and then stored underground in geologically stable rock beds. Now, one other problem with using uranium-235 is it's very limited. Natural uranium only contains about 0.72% of uranium-235, and the remainder is uranium-238. Uranium-238 does not undergo a fission reaction, but uranium-238 can capture fast neutrons and undergo a series we looked at earlier of beta decays and form plutonium-239. Now, plutonium-239 does undergo nuclear fission process if it's bombarded with fast neutrons, but, excuse me, Now, in the use of plutonium-239, we don't need a moderator. We actually use a different type of reactor. It's called the breeder reactor, and I'm not sure I have a picture of that one. I don't. A breeder reactor, and it's designed to produce plutonium-239 from uranium-238. And that breeder reactor uses a mixture of plutonium-239 and uranium-238 as a fuel. And one of the neutrons that's produced from the fission of plutonium-239 to the nucleus is used to sustain the fission chain reaction. So we want to keep this going, right? That's the whole point. While the other neutrons are then going to be used to convert the 238, the mixture that's in there with it, to plutonium-239 to hopefully keep that going. So breeder reactor produces both energy and it produces more fuel. Some famous scientists that really worked on a lot of this stuff might sound familiar. So Becquerel and Curie worked a little bit together, I believe, but Becquerel was basically credited with discovering radioactivity and was given the Nobel Prize in 1903. Marie Curie, that name might sound familiar to you, but she was the first woman to win a Nobel Prize and the first person, man or woman, to win the award twice. With her husband Pierre Curie, they actually worked together for a while. They actually led to the discovery of plutonium and radium, and then after her husband died, the development of X-rays. And she died in 1934 of aplastic anemia, which we consider to be caused from her exposure to radiation. After we discovered radiation, then we wanted to discover what can we do with it. Well, we can do some good things and we can do some pretty bad things with uranium, depending on how you look at it. And Fermi was also working on these things during the time of, we're talking about the late 30s, early 40s was when we're talking about war. So he's actually considered the architect of the nuclear age, or the architect of the atomic bomb. He was one of very few scientists to excel in both theoretical physics and experimental physics. And in 1938, he won the Nobel Prize for, in physics for his work in induced radioactivity. And that's what we just got done talking about with the whole neutron bombardment. And he also discovered transuranium elements. Joliot, he was a French physicist. He was a French guy. I believe Fermi was Italian. That's what it was getting at me. But he won the Nobel Prize in 1935 when he discovered artificial radioactivity. So he actually worked with his wife as well, and they were part of a university team in Paris. The Chicago team was a group of scientists that included Fermi as a team of physicists, and they worked at the University of Chicago. They built a nuclear reactor in a squash court under the south side of the university's football field. They were successful in their experiment, and it was a key step in the creation of the first atomic bomb. We're going to talk about the atomic bomb in a few slides, but also eventually nuclear power. So these scientists made a great leaps and bounds, but also put themselves in great danger. Oh yeah, see, he was Italian. All right, but he received the Nobel Prize in Physics in 1938, and he also had to emigrate to America in 1938. Now, the first controlled nuclear reaction happened in December 2nd, 1942, and this is what he was involved in with the Chicago team under the stadium in the University of Chicago. It produced 500 milliwatts of power. This is how much each country produces via, or how much energy is produced via nuclear energy. I can talk. As of 2011. So we can see that the United States is up there, but again, it makes a lot of people very nervous what we're doing with the waste. So we have a lot of questions, and also transferring fuel rods or something like that makes people very nervous. We have to figure out how to make things safe, and that's our main goal, is safety. Some notable not safe things that have happened over the years. March 28, 1979, one of the reactors at 3 Mile Island in Middletown, Pennsylvania, suffered one of the worst commercial nuclear accidents in the U.S. as of then, when they had a loss of coolant and led to a partial core meltdown. On April 25th and 26th in 1986, Chernobyl, Ukraine. This is actually the world's worst accident as of that point. They had a core meltdown in one of the reactors after the safety protocols were disregarded. So remember, safety protocols cannot be disregarded. They are very important. They are there for a reason, especially in a power plant or in something that's dealing with radioactivity. In March 11th, 2011, after the Tohoku, I did not say that right, earthquake and the tsunami, we had a series of equipment failures and nuclear meltdowns, and those released radioactive material into the Fukushima 1 nuclear power plant. This is actually the largest accident since Chernobyl that has happened. So anytime there's a nuclear and radiation accident, it's defined as an International Atomic Energy Agency. they have an event that leads to significant consequences. We learn every single time we have one of these events, but we learn very hard lessons. So what happened was, we shut something down and we shut it down too fast, or, in this case of the, excuse me, the tsunami, they didn't have, it's not that they had a choice. It was a natural disaster, but the power plant did not get shut down properly. So if you're going to shut down a nuclear power plant, you need to do so following all of the steps. So we have to make sure that we do so safely. Critical mass, we talked about that, is the amount that is perfect to make the power plant run and to continue the reaction to keep it going. And the breeder reactor, we also mentioned this earlier on an earlier slide, is the one that uses plutonium-239 and a mixture of uranium-235 to continue to have the reaction go, but also produce more fuel. This is a nuclear bomb. This is the first bomb. It's the Manhattan Project. This is a gun concept, a little boy. We have uranium-235 here and here. We have a conventional charge that is placed behind this one. You can see it's pointed to go into this one. And then we have the detonator. So the detonator is going to release that and ignite the reaction, because you want to ignite this bomb in the right place. We don't want it going off. The implosion concepts, this is called the Fat Man. This is a hollow plutonium sphere. Here, this blue part. We have a polonium beryllium initiator here in the middle. This was going to start the reaction. And then we just have conventional explosives all the way around that, with the white part being the uranium-238. Remember that we need that neutron from this reaction to get that uranium-238 going. So we talked about fission. What about fusion? So nuclear fusion reactions are the combination. When we combine light nuclei, they're called fusion, and we get tremendous amounts of energy that are generated by these reactions. So this is actually what's happening in the sun. The sun is basically a whole bunch of fusion reactions happening, giving us a lot of heat. Our sun consists of 73% hydrogen, which are protons, and 23% helium, which are alpha particles, and 1% other nuclei, and gives off a vast amount of energy. In fact, I was asked the other day, what would happen if we don't have the sun? I said, we would all die, right? My children are asking about that. So the reactions produce energy to the amounts that we see coming from solar energy in the order of 10 to the 19th kilojoules of energy per second. That is a lot of energy. Now, what are the temperatures? 10 to the 7th Kelvin. That's ridiculously high. All right, we don't want to jump into the sun. You wouldn't get that far. So at these very high temperatures, atoms actually exist in a state called plasma that we haven't talked about yet. And we have nuclei that are unbound. So they're called unbound nuclei and electrons that are happening. Fusion in a hydrogen bomb. So fusion in bombs is also called a thermonuclear bomb. So also called a thermonuclear bomb. The fusion reaction involves deuterium, which is hydrogen 2. Remember that one we talked about, H2. And we also have tritium, which is H3, hydrogen 3. And tritium tritium is being produced from lithium-6. So that's what we see here. We see lithium-6 adding a neutron. So we see we're having this fission reaction where the neutron is bombarding lithium. We get the alpha particle and we get tritium, and that's what's going to start this process. So the lithium-6 deuteride is placed around the plutonium-239 fission bomb, and when the fission explodes, it sets off the following reactions that are like this one here, where we can go to make tritium, or we could also have the products be tritium and, I'm sorry, we were just talking about the other reaction. I just wrote that one. That's the one that's already written there. Where's my eraser? All right, so we can have these reactions here. These reactants are products, oh my gosh, these products produced, or we could also have then our hydrogen, where we have the deuterium and the tritium reacting to produce our alpha particle and a neutron. So there we go. Nuclear transmutation. This is where we're changing one element into another element, and we do so by bombarding an atom generally with a very high energy particle. So something that we've been talking about this whole time, we just haven't really been calling it transmutation, right? So when we talk about transmutation, we're going to be creating some type of unstable nucleus. And we do this a lot in our reactors that we have. Like we have the labs that have particle accelerators, you know, that they're going, and they will shut down at any type of something that's happening, you know, like we have a small earthquake in California, and we got, you know, a particle accelerator in Chicago that's going to shut down because any slight movement could cause that high energy particle to do a lot of damage. So nuclear reactions can be induced. That's what we're doing here, is we're inducing these reactions. And we're doing so by bombarding that target nuclei with some type of fast-moving particle. Usually we call it a projectile, and it's called transmutation. So the first people to work on this were Rutherford and some of his co-workers, and they did this back in 1919 using alpha particles from radioactive sources. So they actually bombarded this into nitrogen-14, and they produced oxygen-17. So remember, oxygen is normally 16. He also bombarded aluminum-27 with alpha particles to produce phosphorus-30, and he was also given the Nobel Prize in Physics for that. So we see that we're making different elements. So these are just a few reactions that you can see. All of the transuranium elements, the elements after uranium, that's what the trans means, have been produced via bombardment reactions. Glenn Seaborg, he actually proposed that the transuranium elements were like another series, like rare earth metals. And in 1940 to 1961, him and his colleagues created 10 new elements. In 1951, they won the Nobel Prize for creating new elements. In fact, we have an element named Seaborgium after Mr. Seaborg. How do we detect radiation, and how do we use radiation? So it depends on what we're doing, but how we detect radiation is through certain different things. Well, it's moved up in ways over the years. So starting with a Geiger counter, we have something that can detect ionizing radiation. A scintillation counter, we have film badges. Some of you might work in places where there is radioactive exposure, and you'll have to wear a certain badge, and you really want to make sure that that badge is working properly. You want to make sure like the plastic piece or the paper, nothing's covering it, because some types of radiation can be blocked by a small piece of plastic being in the wrong place or whatever, and it's not calculating how much radiation you're actually being exposed to. So you want to be careful and make sure that yours is working. Generally at places like that where you work, they'll have you turn in your badge every so often, make sure it's working properly, check it, get you a new one. They're not doing that to annoy you. They're doing that to keep you safe. So make sure you're keeping safe. But ionizing radiation is a particle or a photon that has enough energy to remove an electron when it collides with an atom or a molecule, creating an ion. So that's different. We have a couple different types of radiation, right? It depends if you're working like in a medical field, if you're going to be using certain things that you know you're going to be exposed to radiation, or you're going to be undergoing radiation therapy for medical purposes, that also happens. But we have ways of measuring this. A rotogen, that's how much, like when dosage of X-rays and gamma rays that you're going to be getting, and we have the values in there. A rad is a radiation absorbed dose. So a radiation absorbed dose, or a rad, is a dose of 1 × 10⁻² joules absorbed per kilogram of material. So when you undergo X-rays, we don't want to undergo too many X-rays because maybe you'll start glowing, right? That was always the joke in our kids shows, but no, it can cause a lot of damage. So this is just a couple different units on this slide for measuring the radiation. If you were needing to use any of these, we would give you the conversion factors. Now, half-life, we spent some time talking about half-life, but half-life is just how long it takes for half of the substance to decay. So if we had, I actually posted a video on half-life, so you can watch that, but really we talk about this in terms of carbon dating. We use carbon-14 for that. We can also look at this in terms of, when is it going to be safe to live in Chernobyl again? That happened in the 80s. So is it safe to live there now? I don't know. This is a decay of plutonium showing a half-life. So one half-life here. And then we have a second half-life here, and a third half-life here, and a fourth half-life here. After each half-life, which is 24,400 years, remember how we said thousands of years for those fuel rods? Yeah. The quantity that's present at the beginning is only going to be half after 24,400 years. So not in any of our lifetimes is this going to break down. That's why we're so concerned about what to do with these fuel rods. Radiation sickness is some type of illness that's caused or induced by ionizing radiation. It can range, have a slight, if you catch it early, you can maybe just be nauseous or vomiting, but then you might get a headache and diarrhea, and you might start losing your hair and your teeth, and it's going to reduce the number of red and white blood cell counts. You're going to get it, then eventually, if it doesn't stop, you'll get extensive hemorrhaging, where you start bleeding, and you have often sterility, and eventually death. So when it comes to ionizing radiation, it really depends on these three things. What type of radiation did you come into contact with? What was the length of your exposure is extremely important. And then what is the location or the source? Is it inside or outside of the body? External sources we often have are X-rays and gamma rays. Gamma rays are more harmful than their alpha and beta rays because, remember, they're not deflected as easily. They're not going to be deflected by or attracted to any type of charged plate or anything. We also have internal sources of alpha and beta rays, which would be more harmful because you don't have anything to stop them. Background radiation is something people worry about. We actually have 82% of the radiation that most people come into contact with is natural. One of the biggest things you want to be careful of, especially if you have a basement in Michigan, is that you get it tested for radon. So radon is naturally occurring byproduct. So you want to make sure that you are getting it tested. It can definitely be in our area. Cosmic, 8%, terrestrial, 8%, internal, 11%. And then we have man-made. That's our X-rays, something you might come across at work, nuclear medicine, consumer products, those types of things. So we're not getting most of our radiation from standing next to our microwave, but still, maybe it's not the best idea to stand right next to the microwave. It depends how well your microwave is built and how well it's working, right? You could always get something and try and test it if you're worried about it. How do we apply this? I mentioned you could use the half-life of carbon-14 for radioactive dating. While things are alive, they are constantly replacing their values of carbon-14, but after they die, they will decay, and it'll decay at a known rate because the half-life of carbon-14 is 5,730 years. We can also use this in many medical ways, as most of you are aware of. We have in vitro procedures, in vivo, that are, whatever, it's fine. Inside the body, they have therapeutic procedures that can be maybe something that we're going to use to kill a disease or some type of tissue, or we can also be using it as imaging, as we have MRIs, we have, different types of radiological ways of looking at the body. Maybe you're going to eat something or drink something that is radioactive, and then they'll use a machine to watch it go through your body to get diagnostic information. Radon. Remember I said you should be careful of this. If you're in Michigan, you have a basement, just get it tested. It's a radioactive noble gas, and it's produced naturally by the decomposition of uranium. We do have uranium deposits in the soil. Not that that's necessarily a bad thing on its own, but if it's collecting in your home, you would want to know. It decays by alpha emission, and it produces other alpha emitters, so we want to be careful of that. It is a common household hazard. It depends, but if your home was built over a conventional foundation, over soil that contained trace of uranium. You just want to get it tested and know what you need to do. So this is radon. It's an inhalation hazard, but this is what we're talking about. The radon is going to produce an alpha particle, and it's also going to produce polonium-218. Well, that polonium-218 also produces an alpha particle. So it produces alpha particles itself, but also the byproduct produces an alpha particle, and it can be bad for your lungs. We can use radioactive isotopes as tracers. We can do that in biological systems, but we can also do that in medical procedures, as we discussed, and it's going to provide information on how items are processed. These are some of the tracers we can use: carbon-14, tritium, this is sulfur-35, and phosphorus-32. Tritium can actually tag hydrocarbons. Sulfur-35 they use to tag pesticides and measure airflow. And in phosphorus-32, we can actually measure how well it's being uptake in plants. Diagnostic radioisotopes, as of when I made this, back in the day here, I don't know what year this book was published, but I used the book. We have fluorine-18, phosphorus-32, cobalt-60, technetium-99, and iodine-123 are some of the more common ones. Again, these are often used in diagnostic type things like PET scans or brain scans. We can use them for scanning your thyroid, looking for cancer, or in cancer therapy, as well as looking for cancer. But these are just some of the things that you might come across if you start working in a medical field or if you have to have any procedures done. And that's it.